is Wednesday. The other thing we have going on is our weekly work habit Wednesday. And so what I did today was a little bit of a deep dive into the exam results. So my understanding of how this works is that 2 weeks before the exam, when CASA opens up the time slots, there's a virtual feeding frenzy of people trying to get their preferred slot. And it also seems like there's a conception that getting the later times is better. So there's a lot more demand to get the time slot on Wednesday afternoon or Wednesday evening as opposed to earlier in the week, with the belief that having those couple extra days to study is going to make a difference in your score. So what I did was I divided up the exam scores into the 3 days that you took the exam, Monday, February 17th, Tuesday the 18th, Wednesday the 19th, to try to see if there's any real difference in the exam results as a function of what day you took it. So if you look at the results here, the last day was the most popular day. The most students took the exam on that day. But there's not a huge difference in terms of the numbers for Monday and Tuesday. And what you'll see is that the averages do vary a little bit. So Monday was the lowest average. It turns out Tuesday was the highest average, and then Wednesday was sort of in between, right at the class average. But what I did was what's called a NOVA test on this. Now, I'm not really a stats expert, but they have all these online tools for doing this. And what this essentially does is it takes these 3 groups of students and it compares them in terms of their average and their distribution and all that stuff, and decides is there actually a significant difference between those 3 populations. And so you get an F ratio of 2, I believe, if there was, so a F value of 1 means that the difference is very significant, but the more important value is the p-value here, which came out to 0.11, which means that the result is not significant. Typically, a significant result is one that's defined with a p-value of less than 0.05. You can define significance in different ways depending on what context you're in, but in the sort of standard definition of significance, these results are not significant. So really the conclusion of all this is that while it is true that students who took the exam on Tuesday did the best, there's not really a statistically significant difference between students depending on what day they took the exam. So what this means is that my advice to you is not to worry so much about what day you take the exam. Don't think that, oh, if I take it Wednesday, I'm going to get a better score, because the results don't really bear that out. Try to find a day when you're not super busy, when you have plenty of time to rest up, before before you take the exam, so you're not too rushed, not too hectic, and just sort of schedule it what works best for your schedule, and not really worry about getting the last possible day. Yes.
Does this data include the outliers?
It includes everybody. Yes.
Okay.
So this is all 500 and whatever people that took the exam. And so what you'll notice is that there is a fairly significant standard deviation. So, the averages are around 13, the standard deviations are greater than 3. So there is a wide spread in results for every day. So, but really that sort of further underscores the fact that the standard deviations are all similar, the averages are all similar, is sort of the reason why the differences are not significant, and which is why there's not really any predictive power on your score whatever day you take the exam. So take it on a day that you're, ideally least busy, have time to rest up before the exam, and your schedule's not too crazy. That's sort of my advice for you on this. All right. So that was just some things that mostly for my own curiosity, but hopefully it helps you guys as well understand the effect of what day you take it, which is basically nothing. All right. So today we're going to continue what we started last time, which is dealing with relationships involving moles. So what we ended with last time was how to take a chemical formula and then convert it into the mass percentages. We learned about mass percents way at the beginning of the course, and now we know with mole relationships that if we know the chemical formula of a compound, we can calculate what the mass percentages would be for every element. Today we're going to learn how to go backwards. We're going to start with mass percentages that are given to us and then use that to figure out the chemical formula. Now the issue, though, as we'll get into, is that if you're going to use mass percentages to determine chemical formula, they don't give you necessarily the molecular formula directly. So as you'll recall, when we introduced covalent and ionic compounds, for covalent compounds we write a molecular formula which tells us the total number of each atom in the formula, total number of each atom in a molecule of the compound. And for covalent compounds, remember, we're not going to reduce that to the lowest whole number. So the example we gave in class a long time ago was that NO2 and N2O4, they have the same ratio of nitrogen and oxygen, 1 nitrogen for every 2 oxygens, but those are 2 different compounds. So for covalent compounds, we don't reduce the formula to the lowest whole number, and we call that the molecular formula. But the empirical formula is actually what we're able to get from mass percentages. So the mass percentages won't give us an unambiguous molecular formula. They'll give us the empirical formula, which is the lowest whole number ratio of elements. So the empirical formula of a covalent compound, of a molecular compound, is not a particularly useful thing to think about, but it is what we get if we're using mass percentages to determine the chemical formula, and it is sort of the first step towards getting what the actual molecular formula is. So basically the mass percentages will give us the empirical formula, and then that information in combination with other information that we can have will allow us to determine the molecular formula. So the empirical formula is the lowest whole number ratio of atoms in a compound. For ionic compounds, we always report the formulas as empirical formulas. So remember, for ionic compounds, we always reduce to the lowest whole number ratio of each ion, which means that for ionic compounds, the empirical formula and the ionic formula are the same. But for covalent compounds, this is not necessarily the case. In many cases, the molecular formula can be reduced further to an empirical formula. So to show you the sort of relationships between molecular formula and empirical formula, if you have N2H4, both of those subscripts have a common factor of 2, so we can divide the whole thing by 2, and the empirical formula for this would be NH2. And then for H2O, we can't reduce it any further because there's a subscript of 1 in oxygen, so we don't want to reduce that. So this, in the case of water, H2O, the empirical formula and the molecular formula are the same. So that is sometimes true that the empirical formula is the molecular formula. But for a lot of things, C6H6, which is benzene, that molecule we talked about at the end of chapter 4, this can be reduced a lot. So both coefficient subscripts are 6. We can divide both of those by 6 to get CH as an empirical formula. And then for this compound here with boron, nitrogen, and hydrogen, there's a common factor of 3. So the empirical formula would be BNH2. Now again, to emphasize the point I made earlier, for molecular compounds, you need to know the molecular formula to identify what the compound is. The empirical formula is not unique for a single compound. So there could be, if you have an empirical formula of CH, the molecular formula could be C2H2, C3H3, C4H4, C5H5, or C6H6 as we gave you here. All of those could be the molecular formula with that empirical formula, and all of those would be different compounds. So the empirical formula, as I said, is not a particularly useful thing to talk about for molecular compounds, but it is what we're able to get if we know the mass percentages of the elements, as we'll talk about today. So basically, to go from molecular formula to empirical formula, as I showed you, you just divide by the greatest common factor of all the subscripts in the formula. And just, again, get to the lowest whole number ratio. So that's the relationship between them, but again, what we're going to normally be using empirical formula, the context we're going to see it in is using the mass percentages of the elements to determine what the empirical formula is, which again doesn't tell us everything we need to know, but is sort of the first step to identifying the chemical formula of the compound. So there's sort of 3 steps involved in this process. So what we're going to have is we're going to give you the masses of each element or the mass percents, and what we're going to do is we're going to convert the mass of each element to moles, because remember that the chemical formulas, they tell you the ratio of the atoms in a single molecule, and they also tell you the ratio of moles of each element in 1 mole of the compound. So what we're going to do in this case, if we have the masses of each element or their mass percentages, we're going to convert those into moles. And as we talked about last time, the way you do that is you use the atomic mass of the element as a conversion factor to go between mass and moles. Once you have moles of each element, you're going to want to convert those to the lowest possible ratio. So usually the moles that you get are going to be, fractional decimal numbers, so they're not going to be very convenient numbers to put a chemical formula, but if we can convert those to a simple lowest ratio by just dividing each of those by the smallest number. So each molar quantity we're going to divide by whichever one is the smallest, and that will give us a ratio where one of those is set to 1 and the rest of those are going to be relative to that. And then the third step, which you don't always have to do, is if necessary is all right here, is sometimes when you do steps 1 and 2, you don't get whole numbers. You still get some decimal numbers even after converting them to the lowest ratio. So if you're left with decimal numbers, you don't want to round. We don't want to do too much rounding in these problems. If you're like 0.05 or something away from a whole number, you can round up. If it's something 0.95 or something 0.99, of course, round it up to the nearest whole number. Or if it's 0.01, round it down. But if you have a decimal number that's pretty far in between the whole numbers, like a 0.25 or a 0.33 or something like that, we don't want to round those numbers. We want to multiply the whole thing by a small coefficient, by a small number, to make everything into a whole number. And that will remove fractions and decimals and then allow us to write a chemical formula, which is in terms of whole numbers as it should be. Okay? So as an example of this third step here, let's say we did steps 1 and 2 and we got a formula of N 1.33 H 2.67. Now, one of the most common mistakes people make in these problems is they round. They'll be like, oh, N 1.33 H 2.67, I'll call that NH3. But these are pretty far off from whole numbers, so you don't want to round in this case. What you want to do instead is figure out what is a small number that I can multiply these by to remove the decimals and make them whole numbers. And so if it's 0.33 or 0.67, what's the number we should multiply it by? 3. So if we multiply it by 3, we're going to basically get to N4H8. And that would be, and then we would, so we would get to N4H8. I picked a bad example. But then we can reduce that down to get NH2. That was not a good example because we ended up with a formula that we could reduce further. But if we got, let me try another one that's not so stupid like that. But now you know if you see 0.33s and 0.67s or something or some combination of those, multiply by 3 to get rid of those decimals. Let's say we had something like this. This one I think will come out better. Let's say we had N 1.25 H 3. That should come out fine. Yes, that should be fine. So let's say this is probably not a real compound, but let's say this is the numbers we got. So if you have a 0.25 or a 0.75, what should you multiply by? 4, and that would give us N5H12, which you can't reduce further. So the point is you don't want to do a lot of rounding here. You don't want to round this 1.25 down to 1, unless it's really close to 1, like 1.05 or less. And the numbers that we give you on problems are going to work out pretty well, so that if it's actually supposed to be 1, it'll be like 0.99 to 1.01. It's not going to be that far away from 1 if it's supposed to be 1, as long as you do the problem right. So if you're this far away from 1, if you're 0.25 multiplied by 4, you probably won't have to do anything higher than a factor of probably like 5 or so in most of these problems. So you're going to either multiply by a factor of 2, 3, 4, maybe 5 at the worst. Yeah.
What if it's, can you give an example? What if it's multiplied by 2? What happens if you multiply by 2?
Well, if you multiply this one by 2, you're still going to have a decimal coefficient of nitrogen. It would be 2.5. So you want to make it a whole number. Now, if this was instead N 1.5, then you would just multiply it by 2. So if it's something 0.5, you can multiply by 2 to get rid of the decimal. You basically just need to figure out which factor do you multiply to get rid of any decimals that you have. And if it's something 0.5, the factor would be 2. If it's 0.33 or 0.67, the factor would be 3. If it's 0.25 or 0.75, the factor would be 4. And at worst, if it's like 0.2, 0.6, or 0.8, the factor would be 5. That's probably as high as you'll ever have to go.
So the answer is, so basically, if you said that N 1.5 have 2, well, H3 have 2, that means N3, H6.
It depends on, if this was N 1.5 instead, but then it would be reducible again. So if it was like N 1.5 H4, that would probably be a better example. You'd multiply that whole thing by 2 to get N3 H8. So you have to multiply the whole thing by the factor. You can't just multiply one of the coefficients, so that'll change the ratio. So you take both coefficients and then multiply them by the same factor to get rid of however many decimals you have. So I don't think that's going to come up in any of the examples that I do today, so that's why I wanted to spend a little bit of time on that now. But as a warning, when you're doing homework problems and test questions, don't go crazy with rounding. Make sure you multiply by small factors when necessary to get rid of decimal numbers, okay? So let's see an example of how we do this using just the actual masses of the elements. So there's a compound called vanadyl chloride, which is a rare example of a metal compound that's a liquid at room temperature, sort of this orange color as I'm showing here. And then let's say that we had a sample of vanadyl chloride and we figured out how much of each element is in there. So it contains 1.47 grams of vanadium, 0.462 grams of oxygen, 3.07 grams of chlorine. We want to know what is the empirical formula of this compound. So anytime we have a problem like this, if we're given masses of the elements, the first thing we want to do is convert each of those to moles. So for each element, we're going to convert the mass into moles. So we have 1.47 grams of vanadium, and remember that the way we convert to moles is we use the atomic mass. So we want grams to cancel out, and we want to convert into moles, so we need to figure out what the atomic mass is of each of these elements. All right, so I don't want to come back and forth too many times, but if we look at the elements in this compound, it's going to be vanadium, which has an atomic mass of 50.94, so that's the number we would use to convert the mass of vanadium to moles. Oxygen is 16, we saw that out last time, and then chlorine is 35.45. So from the periodic table, we're going to use those three atomic masses to convert each element's mass into moles, and we want the atomic mass to be in the denominator to make sure that grams cancel out. So for vanadium, as we said, it's 50.94 grams per mole. Grams cancel out, and that gives us 0.0288 moles of vanadium. We're going to do the same thing for the other two elements. So for oxygen, we have 0.462 grams. And then we're going to divide by the atomic mass, which is 16, to convert grams into moles, and that gives us the same number pretty much, 0.0289. So we can tell already that our chemical formula would have equal numbers of V and O. But then if we do chlorine, Cl, we're told that we have 3.07 grams of chlorine in the compound. And when we convert that to moles, we get a different number this time. Sorry, it should be 35.45. I wrote that wrong. So it's 35.45 grams per mole for chlorine is the atomic mass. And when we multiply that across, we get 0.0866. So these are the moles of each element that we have. And again, to find a chemical formula, what we want to find is the lowest whole number ratio of those moles. That's what we, so the chemical formula could technically be written as this: V 0.0288, O 0.0289, but conventionally we don't write chemical formulas with decimals, we write them with whole numbers. So to convert these decimals into whole numbers, we're going to divide all three of these coefficients by whichever of these numbers is the smallest. So the smallest number was 0.0288, so we're going to divide all of those by 0.0288. Whenever you get mole ratios, whether you're going to divide them by a common factor or multiply them by a common factor, you have to do the same thing to all of them to keep the ratio the same. So we divide all three of these by the smallest number, and then what that comes out to is, again, with very little rounding necessary, VOCl3. Okay, in this case, we didn't end up with any decimal numbers in our formula after this point, so we stop here. We don't have to multiply that by any sort of factor. So the empirical formula for this compound is VOCl3. That's also, as it turns out, the chemical formula of the compound itself. Okay. All right. So any questions on how I did this one? All right. So we'll move on to one that's very similar. In this case, we're going to be doing mass percents, though. So we have a binary compound consisting of boron and fluorine, and it's 15.94% boron by mass. So that's all I gave you, and I want you to determine the chemical formula. So a couple things is reading the problem with some key words here. Remember that binary means it only has two elements, and we're telling you that those two elements are boron and fluorine. So those are the only two elements in the formula, and we're giving you the mass percent of boron. And so remember, if we have mass percents, they're going to all add up to 100. So if we want to find the mass percent of the other element, which is fluorine, which we're going to need to solve this problem, the total was 100%, and we can subtract then the mass percent of boron. So anytime you're dealing with mass percents, if it's a binary compound, the two should add up to 100. So if you have one of them, you can find the other one quite easily. So by subtraction, we figure out that the mass percent in terms of fluorine is 84.06%. All right, so we have a compound that's 15.94% boron, 84.06% fluorine by mass. In this case, we're not dealing with actual masses, we're dealing with mass percents. But we don't have to really do anything different here. What we're going to do is, if we're given mass percents instead of actual masses, we're going to assume that we have 100 grams of the compound. Okay, because remember that mass percentages are how many grams per 100 grams of the compound. So if we assume 100 grams of the compound, from the percentages, we know that 100 grams of compound has 15.94 grams of boron and 84.06 grams of fluorine, and then we can just use those numbers as our starting masses and follow the same steps that we did in the last problem. So if we assume 100 grams of compound, to find how many moles of boron are in that 100 grams of compound, there's going to be 15.94 grams of boron in 100 grams of compound. That's why the mass percent is 15.94. And then we're going to use atomic masses to convert these into moles. So we're going to have boron and fluorine in this case. So boron is 10.81 grams per mole. Fluorine is 19 grams per mole. So those are the two atomic masses we're going to use. And we're going to do the same thing we did last time, which is convert each mass number to moles. So 1 mole of boron has a mass of 10.81 grams, and that's how we're going to write it to make sure that grams divide out. And so we're going to get 1.474 moles of boron. And then if we do the same thing for fluorine, we figure out up here that the mass percent of fluorine is 84.06, meaning there's 84.06 grams of fluorine in 100 grams of compound. And then we're going to do 1 mole of fluorine has a mass of 19 grams. And we get 4.424 moles of fluorine. All right, so just like before then, what we're going to do is we can write the formula with these decimal numbers, but it's in the non-standard form, and we're just going to divide both of those subscripts by the smallest one, which is 1.474.
Question.
Yeah?
For a binary, can't you just divide one over the other and take the ratio?
Well, that would give you the mass ratio. We're trying to find the mole ratio.
Correct.
So you could do that with the moles, but you can't do that with the masses directly.
Gotcha.
So we're going to get, in this case, once we do the mole ratios, we get BF3. That's what we're looking for here. Okay? All right, so same steps as last time, just this time we gave you percentages instead of masses, so we're going to assume 100 grams and go from there. All right, the last thing I want to talk about related to this is, as we said, when you do this approach, when you use either masses of each element or mass percentages, the last two problems we did, what you get is an empirical formula that doesn't unambiguously tell you a molecular formula, because every compound that has the same empirical formula, we talked about the ones with CH, if it was C2H2, C3H3, C4H4, C5H5, and so on, all of those different compounds would have the same mass percentages or the same relative masses. So when you use masses to determine a formula, all you can get from that is the empirical formula. If you want to find the molecular formula, the other information you need is the actual molecular mass, which there are experimental techniques to find that. So typically, if you want to find the molecular formula of a compound, this is a little bit old school. We don't really do it this way anymore too much, but in practice what you can do is you can use mass percentages to find the empirical formula, and then if you know the molecular mass, you can use that to unambiguously determine what the molecular formula is. And the way that works then is best described with an example. So your molecular mass is going to be the empirical mass, which is the molar mass of the empirical formula, multiplied by some small whole number. Because remember, your molecular formula is going to be some whole number multiple of the empirical formula, so the molecular mass and the empirical mass will be related by that same whole number multiple. So as an example, if we have a compound with a molecular formula of CH2, and there are thousands, if not millions, of compounds in the world that have the empirical formula CH2. So this is not anywhere close to identifying a unique compound. But if we also know that the molecular mass is 70 AMU, we can figure out what the molecular formula is. So what we're going to do is, for the empirical formula, we're going to determine what the empirical mass is, which is just going to be whatever mass corresponds to this formula. So we have 1 carbon in the empirical formula times its atomic mass of 12.01. Our empirical formula has 2 hydrogens, and the atomic mass of hydrogen is 1.008. So we're going to find what's called the empirical mass of this compound, just the sum of the elemental masses, the atomic masses that are in. And what we get is, without worrying too much about decimal places here, 14 AMU. And then what we're going to do to figure out what factor are we going to multiply our empirical formula by is we're going to divide the two. We're going to take the molecular mass that we're given and then divide it by the empirical mass. And And so our molecular mass is 70 AMU, or 70 grams per mole. And then our empirical mass is 14. And when we divide those two, we get 5. And so what that means then is that our molecular formula is a multiple of the empirical formula times 5. So our molecular formula then is going to be CH2, which is the empirical formula, taken 5 times, which means our molecular formula is C5H10. Okay? So as I said, there's so many compounds that have the same empirical formula, C3H6, C4H8, C6H12, and so on. Anything that has a 1 to 2 ratio would have the same empirical formula, but if you know also what the molecular mass is, you can unambiguously identify this as the correct molecular formula, because the ratio of the molecular mass to the empirical mass would be the factor that you're going to multiply the empirical formula by to get the molecular formula. So with that additional piece of information, the molecular mass, you can, in addition to finding the empirical formula, also find the molecular formula. So let's put it all together and see how it works in total. So in this problem, we have a compound that is 28.18% mass manganese, 30.80% carbon, and 41.03% oxygen, and has a molar mass of 389.98. Determine its molecular formula. Now, even though this is a metal-containing compound, something that's not really important for this course is that with transition metals like manganese, you can form what are sort of covalent compounds that have molecular formulas involved. So we're going to do that here. So what we're going to do first is we're going to find the empirical formula using the mass percents. So just like we did in the previous problem a couple slides ago, we're going to assume that we have 100 grams of compound, and we're going to find the moles of each element. So for manganese, if we assume 100 grams, there's 28.18 grams of manganese in the compound, and then the atomic mass of manganese, I don't want to flip back and forth a million times the periodic table, but if you have the periodic table in front of you, you'll see that Mn has an atomic mass of 54.94. So if we divide by that number, that'll give us the moles of manganese in 100 grams, which is 0.5129 moles. For carbon, we do the same thing. In this case, the percentage of carbon is 30.8, so we have 30.80 grams of carbon in 100 grams of the compound, and the atomic mass of carbon is the familiar 12.01 number that we've seen a bunch of times already. All right, so that's moles of carbon, which is 2.564. And then finally for oxygen, we have to take its mass percent, 41.03, assume that we have that many grams of oxygen in 100 grams, and convert it to moles using the atomic mass of oxygen, which is 16. And we get about the same number, 2.564. All right, so to find the empirical formula, we're going to take each of those molar amounts, and I'll just round them a little bit because we don't need that many decimal places to do this. So manganese 0.513, carbon 2.56, oxygen 2.56, and we're going to divide by the smallest one, which is 0.513. So we're going to divide all of those by that same number to get them down to a ratio. And this time it also works out with whole numbers, so we get MnC5O5. All right, so that's the empirical formula of this compound. But if we want to determine the molecular formula, we also have to use the molar mass and compare it to the empirical mass. So the other piece that we need to calculate is the empirical mass. So now that we know the empirical formula, we can determine the empirical mass by just adding up all of these atomic masses, manganese plus 5 times carbon plus 5 times oxygen. So we use the atomic masses up above, so those numbers are already there. So manganese is 54.94. I'm going to leave out units if you'll forgive me. Carbon is 5 times 12.01. And then we have 5 oxygens with an atomic mass of 16. And so what we get for the empirical mass is 195 grams per mole. And then if we divide the empirical mass by the molar mass, sorry, other way around, divide the molar mass by the empirical mass, we get about 389.98 is the given molar mass that's given to us in the problem. There's no way to, in this case, determine that otherwise. And then we divide that by the empirical mass of 195, and you can probably see that this is pretty close to a ratio of 2. And so what that means is that our molecular formula is 2 times the empirical formula, because our molar mass is twice the empirical mass. So we're going to take this to find the molecular formula and multiply the whole thing by 2, and we get Mn2C10O10, and that would be the correct formula for this compound, which would be, if you want to know the name of it, dimanganese decacarbonyl. Okay. So that's going to be how we do that, putting it all together. Mass percentages give us empirical formula, and then with the molar mass, we can also convert that to a molecular formula. Okay? So any questions on what we've covered so far? All right, so the next thing we're going to talk about is a slightly more advanced method for determining empirical formulas called combustion analysis. And this we actually do use today in research, so it's actually it's an old technique, it's been around for a while, but we still use it today. We don't use it so much to determine molecular formula, but we use it to confirm the molecular formula that we think we have, and also confirm that the compound doesn't have any impurities in it, but it's still a valuable technique. So the way that this technique works is, we're going to talk a little bit more about combustion reactions in the next section of this course, but what you're going to do is you're going to take some organic compound. An organic compound typically has carbon, hydrogen, and possibly some other stuff in it, and you're going to burn it. You're going to literally set it on fire. Now, when you burn an organic compound, the 2 products that you get are CO2 and water, plus if there's other stuff in the compound besides carbon and hydrogen, you'll get some other products possibly as well, okay? So what you're going to do then is, from the amount of CO2 that you form, so you're going to know how much organic compound you burned, you're going to measure the mass of the compound that you burned, you're going to measure the mass of each of the products that comes out, in particular CO2 and water being the important ones. And then what you're going to do is, using the mass of CO2 that you form, you're going to extract how much carbon there is, because all the carbon that was in your compound when you burn it is going to go into CO2. And similarly, all the hydrogen that was in the compound that you burned is going to end up in water, so you're going to use the mass of water that is produced to figure out what mass of hydrogen was in the compound. And then if you have other stuff, often oxygen in the formula, so oxygen gets distributed a lot, because when you burn a compound, you burn it in the presence of oxygen, and then the oxygen that's in the compound plus any oxygen you burn it with goes to both CO2 and water. So we can't directly determine the mass of oxygen in the compound, but what we can do for oxygen or anything else that's in the compound is we can find the mass of that stuff by difference. So we know the total mass of compound that we started with. We know how much carbon is produced based on how much CO2 we get, and we know how much hydrogen is there based on how much water we get, so we can subtract the mass of carbon and the mass of hydrogen to get the mass of anything else that was in our compound, okay? So for this to be practical and to actually be able to determine a chemical formula easily, there can only be one other element in the compound. If there's more than one other element, you can just know the total mass of those other elements, but not the mass of each one. So typically, most commonly, the other element is oxygen, as I said, but if there's one other element in the compound, you can use, by difference, by subtraction, you can figure out how much mass of that there is as well, okay? And so what this allows us to do, and the reason it's an important experimental technique, is we can determine the empirical formula of an unknown compound. So this is another technique for doing it. It's a little bit more indirect. But we're going to burn the compound and use the data that we get, the mass of each product that forms from the combustion. We're going to use that to determine an empirical formula, and we don't even need to know anything about the compound before we start, except for what elements are in it. Okay? So we'll go through an example of this, but basically the way this works is, once you have the mass of each element, mass of carbon, mass of hydrogen, mass of anything else that's in there, we're going to use the same approach we've already covered today to convert those masses into an empirical formula. So it's basically just a more involved process for getting an empirical formula. We don't directly get the masses of each element. We have to use some other information to get that. All right, so here's an example of this. This type of problem is best demonstrated with an example. So we have a compound consisting of carbon, hydrogen, and bromine. So the bromine would be what I called on the last slide, the other stuff that's in the compound. Carbon and hydrogen, we can always figure out their masses from the combustion data. The other stuff, in this case, is bromine. And we burn this compound. And when we burn this compound, what we get, when we take 5 grams of the compound and burn it, we end up with 0.871 grams of carbon dioxide as a product and 0.179 grams of water. What is the empirical formula? So the first thing we need to do is we need to find the mass of each element. Now, technically speaking, we want the moles of each element, but as we said, if you have another element besides carbon and hydrogen, you need to find its mass by difference. So in this case, we need to find the masses of carbon and hydrogen first to be able to find the mass of the other thing that's in there. So we're going to find masses of carbon and hydrogen first. And the way we do this is recall that in a combustion reaction, all of the carbon ends up in CO2. So we have 0.871 grams of CO2. We want to know how much of this 0.871 grams is carbon. Now there's a few different ways of doing that conversion. We could use mass percents, we could use other possible approaches, but the way that I'll do it uses mole conversions that we've been talking about the last two lectures now. So what we're going to do is if we have 0.871 grams of CO2, the first thing we can figure out is how many moles of that do we have. So as I said, when in doubt, convert to moles, and that's going to be the first step here. 1 mole of CO2, we're going to use the molar mass of CO2. So the molar mass of CO2, just to remind ourselves how we do that, is carbon, which is 12.01, plus 2 oxygens, which are 16. So we get about 44.02. So that's the molar mass of CO2. So we're going to use that to figure out how many moles of CO2 we have. And now that we know how many moles of CO2 there are, we can figure out how many moles of carbon we have because we have the chemical formula CO2, which tells us that in 1 mole of CO2 we have 1 mole of carbon because there's a subscript of 1 that's implied on carbon, and 2 moles of oxygen. So from the chemical formula we know that each mole of CO2 has 1 mole of carbon. And then once we have moles of carbon, we can figure out how many grams that is by using the atomic mass of carbon. So this time we want to go from moles to grams, so we want moles to cancel. So we're going to put the atomic mass of carbon, which is 12.101 in the numerator, over 1 mole. And that allows moles to cancel out. Now we have grams of carbon. So there's a few steps, but hopefully steps that are familiar to us by now or becoming familiar, and we get 0.238 grams of carbon. So of the 0.871 grams of CO2 that we produced, 0.238 grams of that is carbon. And that's how much carbon then was in the compound that we burned, because all the carbon goes to the CO2. We're going to do a very similar set of steps for hydrogen to find its mass. So we produce 0.179 grams of water. And same as before, what I'm going to do first is convert grams of water into moles of water. So we're going to divide by the molar mass of water, which is 18.02. Now the only difference here is if we want to find moles of hydrogen in 1 mole of water, remember that the formula of water is H2O, so that tells us that 2 next to hydrogen, that there's 2 moles of hydrogen for every 1 mole of water. So that's the only small difference here, is that we're going to multiply this by 2 to figure out how many moles of hydrogen there are. All right, so that gives us moles of hydrogen, and then the atomic mass of hydrogen, which is 1.008, pretty close to 1, allows us to convert the moles of hydrogen into grams of hydrogen. And again, we're going to multiply in this case so that moles cancel out, and that gives us grams. And so what we get in this case is 0.0200 grams of hydrogen. All right. And then finally, to find the mass of the other element, in this case bromine, or whatever other element we would have in the compound, we're going to do that by difference. So in this combustion experiment, we burned 5 grams of the compound, so that's the total mass of the compound, of all the elements in the compound. So that's how much compound we burned. And then we can subtract the masses of the other 2 elements to figure out how much of this is bromine. All right, so as we just found out, there's 0.238 grams of carbon, and there's 0.0200 grams of hydrogen. So by subtraction, we can figure out that there is 4.74 grams of bromine. So most of the mass of this compound is bromine. Bromine is a very heavy element, so that's not perhaps surprising. It has a very high atomic mass. But now we have the masses of all 3 elements. Carbon, which we got from CO2, hydrogen, which we got from the water that was produced, and then bromine, which we got by difference. And so now at this point, we can do the same series of steps that we've been doing all day today to figure out if we have this mass of each element, what's the corresponding empirical formula. So the moles of carbon, we're going to find now moles of each element. in this case, what we're basically doing is just undoing the last step of the calculation we did for carbon. So it's 0.238 grams of carbon, and now we're just going to divide by the atomic mass to go back to moles. So as I said, we're basically just undoing this last step here, but we needed the mass of carbon to be able to figure out the mass of bromine, so that was necessary to do it that way. All right, so we're going to divide by the atomic mass to figure out how many moles of carbon that is. That's 0.0198. Same thing for hydrogen. We have 0.0200 moles of H, and the atomic mass of hydrogen is 1.008, so we're going to divide by that number to get moles of hydrogen. Whoops, I did that wrong, didn't I? That's grams of H. Getting ahead of myself. But the numbers aren't too different because the atomic mass of hydrogen is basically 1. So it's 0.0198 moles of hydrogen, pretty much the same as the mass because the atomic mass is 1. And then finally, to get the moles of bromine, the last element which we found by difference, we saw that there was 4.74 grams of that element. And its atomic mass, I'm not going to go to the periodic table, but if you look at the periodic table for bromine, the atomic mass is 79.9. All right, and so what we end up with is 0.0593 moles of bromine. All right, and then the last step is to convert these into the smallest ratios by dividing by the smallest one. So we have 0.0198 for carbon, 0.0198 moles of hydrogen, and for bromine we have 0.0593. We're going to divide all of those by the smallest, which is 0.0198. And we get CHBr3, which is called bromoform. Okay? So that's the empirical formula we get. So those combustion analysis problems, they do have a lot of steps involved. They're a little bit time-consuming and tedious, but none of the individual steps I think are particularly difficult. It's just a bunch of mole and mass conversions that we've been talking about the last time, putting a lot of them together to be able to finally work out what the empirical formula is. All right, so any questions on that type of problem? Yes?
So for the mass of carbon, multiply it by 1 carbon and 1 CO2. Can you explain that?
Yeah, because the formula of CO2 is C1O2. We don't put the 1 in the formula, but so what that tells us is that for every mole of CO2, we have 1 mole of carbon. So the subscripts in the chemical formula tell you how many moles of each element you have per mole of compound. So that's why in this case we just multiply by 1 because the formula of CO2 just has 1 carbon in it. But down here we multiply by 2 because the formula of H2O has 2 hydrogens in it. So that's the difference there. Yes, up there?
Yes. The question, kind of add on to his question. So are we assuming as a law that C is going into CO2 as a constant for the test problem unless no otherwise?
Yeah, so if you do a perfect combustion, as it's called, all of the carbon that's in the compound you burned ends up in CO2. So in an ideal combustion reaction, the only products are CO2 and H2O. Now, if you have some other element besides carbon, hydrogen, and oxygen, you'll form something else as well. But in an ideal case, all of the carbon ends up in CO2, all the hydrogen ends up in water. Okay?
So for this, we always assume ideal conditions.
Yeah. There's no other way to do it. Okay. So any other questions? All right, so let's move on then. So we're going to transition now into talking about chemical transformations, chemical reactions, which we've seen a little bit of in this class, but we're going to sort of formalize it more now and then start doing some numerical calculations that relate amounts of substances that are involved in a chemical equation, chemical reaction. So the way that we represent a chemical reaction is with a chemical equation. Because our book does things in a weird order, we've already seen these to some extent. But so we should mostly be familiar with this already, but in a chemical equation, you have two sides, left and right. So the reactants are on the left side, and these are going to be the elements or compounds that are consumed in the reaction. And they, as I said, appear on the left side of a chemical equation. So in a chemical reaction, we're taking some collection of elements and compounds, we're reacting them with each other and turning them in to some other collection of elements and compounds. So the ones that we're putting into the reaction are the reactants, And then whatever's formed when those elements and compounds rearrange themselves into new products, those are called the products of the reaction into new. And so the products are the elements or compounds that are formed during the chemical reaction. And in a balanced chemical equation, each reactant and product is going to have a coefficient in front of it, a numerical coefficient in front of the formula for the element or the compound. And the coefficients, they're going to be typically whole numbers. They don't have to be. It's not wrong to have fractional coefficients, but usually when we ask you to balance chemical equations, we want you to do it with whole numbers. And they're going to be numbers that are in front of each symbol, each chemical symbol or each chemical formula, that tell you the number of atoms or molecules or moles of each of those that's involved in the reaction. So they tell you the number of either the number of atoms and molecules or the number of moles of each species in the chemical reaction. Sorry, I wrote each twice. So just like chemical formulas can be interpreted in terms of either atoms or moles, as we said, if the formula is CO2, that you could either interpret that as one molecule of CO2 has one carbon atom and two oxygen atoms, or you can interpret that as 1 mole of CO2 has 1 mole of carbon and 2 moles of oxygen. Similarly, the coefficients in a chemical equation can be interpreted in terms of atoms and molecules or number of moles. So you could say this many molecules react with that many molecules to form this many molecules of product, or the more useful way of interpreting it in most cases is this many moles of each species react to form this many moles of product. Yes? Species would be a reactant or a product, a chemical compound or chemical element that's in a chemical reaction. Species is a stand-in for chemical substance. It's just a stand-in for that. So it means a chemical substance that's either a reactant or a product. Let me just change that to substance perhaps to make it clearer, but yeah, it just means something that's in a chemical reaction as a reactant or a product. Okay? And so the coefficients tell you in the most, again, the way we're going to typically interpret this is in terms of moles, the relative number of moles of each substance that's in the chemical equation. But you can also think of it in terms of, at the atomic level, atoms and molecules as well. And when we balance a chemical equation, remember one of the first things we learn in this course, the law of conservation of mass, or the law of conservation of matter, which is that atoms are neither created nor destroyed during a chemical reaction. And so what that means is that if your chemical equation has 12 moles of carbon on the left side, on the reactant side, it will also have 12 moles of carbon on the right side. So for any element that's involved in this chemical equation, you need to have the same number of atoms or moles of that element on the left as you do on the right side. That's what's called a balanced equation that has the same number of moles of each element on each side of the equation, because you're not going to create or destroy atoms during a chemical reaction. All right, so to take this a little bit further and talk some more things about how we balance chemical equations. So first we're going to arrange the reactants and products. If we don't write them out for you, if we just, if we just write the chemical reaction in terms of a word problem, you have to make sure that you put the reactants and the products on the correct side. So reactants on the left, products on the right with an arrow in between. And then we want to add the coefficients. So remember, we don't change the chemical formulas of reactants or products to balance. The chemical formulas of the reactants and products are fixed at whatever they are, but we're going to add coefficients in front of the chemical formulas to make sure that the number of atoms of each type is balanced on both sides. Okay? So we're going to add coefficients, and there's not always a right or wrong way to do this. A lot of times there's multiple ways you can approach this, but what I like to do is find whatever the most complex reactant or product is, the one that has the most atoms in it, the most different types of, the most complex formula, and we're going to set that to 1. All right, so we're going to set the most complex. In some cases it's ambiguous which one's the most complex, but in a lot of cases it's pretty clear. We're going to set that, again, I'll use the word species here to represent reaction or product. We're going to set that to a coefficient of 1, and then we're going to balance everything else relative to that. All right, and so we're going to adjust then coefficients on both sides of the arrow if necessary to make sure that the atoms balance on each side, to make sure that we have the same number of each type of atom on the left as we do on the right. So in this chapter, when we're first introducing chemical equations, we're primarily going to just balance them by inspection. We're going to just give you reactions and products, and you're going to just monkey around with the coefficients until the whole thing is balanced. There's not going to be a real systematic way to doing most of these. In chapter 6, we'll introduce a few reaction types where there is perhaps a more systematic way of going about the balancing. In particular, one reaction type especially where we have a real set approach for balancing it. But in the ones that we're going to start with, we're going to mainly just do it what we call by inspection. Just change the coefficients, adjust them here and there until it looks like everything is balanced. Now, it is good to check yourself after you've done the coefficients, make sure that the number of atoms on the left and the number of atoms on the right are the same of each type. So if you have time on an exam to check your work, it's always good to do that. And in this case, it is good to make sure that everything works out. And then the other thing that you will often see in chemical equations, we've seen it already a little bit when we talked about electron affinity and ionization energy, is the state of matter for each chemical reactant or product. So it'll be a little subscript in parentheses next to the chemical formula, S for solid, L for liquid. This is not terribly important, but if you see these, I don't want you to be confused by them. G for gas. So solid, liquid, or gas. There's some other ones that we'll see in the next chapter as well, or at least one other one. And so that's going to be also present in many chemical equations. I'm not going to make a big deal out of it. A lot of times I'll just leave them out and not really worry about them too much. They don't have to be there, but they are in many cases. All right, so the best way to do this is to just practice how to, a few different types of reactions. So this would be, again, we're going to formalize it more in the next chapter, but this would be a combustion reaction here. So if we have ethane, which has a formula C2H6, combustion means that we're going to burn it in the presence of O2, oxygen, and we're going to form CO2 and water as products. And because the reaction that we're burning only has carbon and hydrogen in it, the only products we form are CO2 and water. So to balance this thing, we have to choose something to set as the most complex. And what you'll see here is that C2H6 has the most atoms in it. It has a total of 8 atoms in the formula, 2 carbon, 6 hydrogen. The rest of them are much smaller molecules. O2, CO2, H2O have no more than 3. So what I'm going to do to start is I'm going to set this with a coefficient of 1. Now typically we don't write coefficients of 1 in chemical equations. If there's no coefficient, it's implied to be 1. But I'm just going to write that there to remind myself that I'm setting this as a coefficient of 1. And then we're going to do the rest from there and balance from here. So when you're balancing chemical equations, one thing that's helpful to do is find elements that only appear once on each side of the equation. So we only have 3 elements in this whole equation, carbon, hydrogen, and oxygen. But if you look at oxygen, you'll see that oxygen appears once on the left, but it appears in both of the products, CO2 and water. So we don't want to try to balance oxygen first because there's going to be unlimited combinations of coefficients on CO2 and water and O2 that would balance oxygen, but those aren't necessarily going to result in balancing carbon and hydrogen. So what we want to start with is an element that only appears once on the left and once on the right, which would be true for both carbon and hydrogen. So carbon only shows up in this reaction here, C2H6, and it only shows up in the product CO2. And so if we have one C2H6 that has a total of 2 carbons in it, we need to have 2 carbons on the right side, so that gives us a coefficient of 2 in front of CO2. Okay? We don't change the formulas, we just add coefficients in front of them, and so now we have a total of 2 carbons on each side. And then we're going to do the same thing for hydrogen. This reactant here has 6 hydrogens, so we have 6 hydrogens on the left. We also need to have 6 on the right. The formula for water is H2O, so if we put a coefficient of 3, that gives us a total of 6 hydrogens. 3 water molecules, each with 2 each, okay? All right, and then so that takes care of carbon and hydrogen. At this point, we don't want to adjust these coefficients anymore because we've now balanced carbon and hydrogen, so anything we do to these is going to screw that up. But if we look at oxygen on the left side, we need to make sure that that's balanced. So what we have now on the right side of the equation for oxygen is 2 CO2s, each with 2 oxygens in them, plus 3 waters that each has 1 oxygen in them. So we're a total of 7 oxygen atoms in the right side of the equation. So we need to make sure we also have 7 oxygen atoms on the left. So if we have O2 that has 2 oxygen atoms each, we need 3.5 oxygen molecules, O2, to make sure we have a total of 7. So the coefficient we're going to initially put in for O2 is 7 halves, or 3.5. 7 halves times 2 is 7, so now we have 7 oxygens on each side. Now, as I said, it's not wrong to balance a chemical equation with fractional coefficients, but conventionally we want to use whole numbers, and usually on test questions or homework questions, we will specify that you should balance it with whole numbers. And so what we're going to do then is we want to make all these whole numbers. So just like we did for empirical formulas, we want to multiply all of these coefficients by some small factor that gets rid of any fractions. So if you have a fraction of 7 over 2, what are we going to multiply all these by to get rid of the fraction? Yes, we're just going to multiply them all by 2. Now remember, because this is a balanced equation now, we have to multiply every single coefficient by 2. We can't just multiply one coefficient by 2, or that'll throw out the balance. We have to do every single one. So this 1 becomes a 2, this 7 halves becomes a 7, this 2 becomes a 4, this 3 becomes a 6, and this should be then the correct balanced equation. Coefficients are in their lowest whole number ratios as they should be. They're all whole numbers. As I specified, we're usually going to do. So then the last thing to do is to check to make sure that everything balances out. So on the left side of the equation, for carbon, we have 2 times 2 ethane molecules, each with 2 carbons, so that's 4. And on the right side of the equation, we have 4 CO2s, each with 1 carbon, so that's a total of 4. So that checks out, 4 carbon atoms on each side of the arrow. If we do the same thing for hydrogen and oxygen, for hydrogen on the left side we have 2 times 6, 2 molecules of C2H6, each with 6 hydrogens in it, so that's a total of 12. And then on the right side, we have 6 water molecules, so 6 times 2, 6 molecules, 2 hydrogens each, total of 12. So those check out. And then finally for oxygen, which is the more complicated one, on the left side we have 7 O2s, so 7 oxygen molecules with 2 each is 14. And then on the right side we have 4 CO2s that have 2 oxygens each, plus 6 waters that each have 1 oxygen, so 4 times 2 plus 6 times 1 is 14. Everything checks out. We have the same number of each element on the left and the right, and so this is going to be then the final balanced form of our equation. Okay? Any questions on how I did that? All right. Let's do another one. So another type of problem that you'll have to deal with at times is we're not going to give you the reactants and products directly. We're going to write it out for you in words, and you have to arrange things, again, in some cases going from names to formulas, or in this case, we gave you pretty much the formula of everything. So Fe2O3, which is rust, is formed by the reaction of iron and oxygen gas. Write a balanced equation for the formation. All right, so the reactants are going to be iron and oxygen. Iron is just Fe, oxygen is O2. And those two react to form Fe2O3. So this is a relatively simple reaction, just 2 reactants and 1 product. And once again, we're going to set the most complicated thing to a coefficient of 1. That's clearly Fe2O3, which has 2 different elements in the formula and a lot of different atoms. So we're going to set that to 1, and then make sure everything on the left side is balanced. So on the right side, we have 2 irons. So we need a coefficient of 2 to make sure we have also 2 Fe's on the left. And then for oxygen, we have 3 O2 to make sure we have a total of 3, means we need 1.5 molecules or moles of oxygen, or 3 halves. 3 halves times 2 is 3, 1 times 3 is 3. So this is all balanced out, but we still have a fractional coefficient, so if we specify whole numbers, we should again multiply this whole thing by 2 to get rid of the fraction. We get 4 Fe plus 3 O2 goes to 2 Fe2O3. So that would be the reaction balance with whole numbers. These are the smallest ratio, and we can once again check ourselves to make sure that the elements are balanced on each side. All right, so on the reactant side for Fe, iron, we have 4, and then each iron is just a single atom, so 4 times 1, which is 4. And on the product side, we have 2 Fe2O3s. Each one has 2 irons in it, so 2 times 2 is also 4, so that checks out. And then for oxygen, On the reaction side, we have 3 O2s, so a total of 6 oxygen atoms. And then we have 2 times 3, 2 FeO2 O3s with 3 each, also a total of 6. Okay, so a quick check shows that there's only 2 elements in this case, and they're both the same on the reactants and the product side. All right, last one we'll do here, which looks more complicated than it is. So the compound cesium-4, rhenium-6, selenium-8, I6 is formed by heating rhenium, selenium, cesium iodide, and I2 to 800 degrees Celsius for about 4 days. Write the balanced reaction and then determine the sum of the coefficients. So this is just giving you an example of how we sometimes set up the problems in Blackboard, where we'll ask you to balance the chemical equation, and then we'll either ask for coefficients on the reactant side, coefficients on the product side, or in this case, the sum of the coefficients. So just, again, different ways of asking to, how to report the answer. So the reason that I picked this one to show you guys is because this was the very first chemical reaction I did when I did undergraduate research. So as they say, you always remember your first chemical reaction, and this was the first one that I did, so it's very special, has a very special place in my heart, so I was hoping to share it with you guys. Okay, so here we're telling you that we have 4 reactants in this case, all heating up together to form a single very complex product. So on the reactant side, we're going to have Re, which is rhenium, plus Se, which is selenium, plus cesium iodide, and then I2, elemental iodine. And then on the product side, we just have this one compound that's formed, cesium-4, rhenium-6, selenium-8, I6. All right, it's what's called a cluster compound. It has a pretty cool structure if I were to show you. And this is what it looks like. It's kind of a nondescript sort of grayish black powder, but when you hold it up to an ultraviolet light, it glows bright red. This was sort of how I got drawn into inorganic chemistry, was seeing that. So it's very cool. You had to be there, I guess. All right, so then this is the reactions and products, and once again, we're going to follow the same approach for balancing. We're going to find whatever the most complicated species is and set it to 1. I think it's very clear that this is our most complex one. And then once again, we want to find elements that only appear once on each side. So looking at what we have, 4 elements in this case, cesium, rhenium, and selenium only appear once in the product as well as once on the reactant side. We want to balance iodine last because iodine appears here on the product side, but it appears in 2 of our reactants. So we don't want to try to balance iodine first because we don't know which combination of coefficients on these 2 is going to be correct to also make sure that the other elements are balanced. So we'll do the other ones first. So in the product, we have 6 rhenium, so we need a coefficient of 6 there. We have 8 selenium, so we need a coefficient of 8 there. And then we have 4 cesiums, so we need a coefficient of 4 there. And now what we look at is our product has 6 iodines, I6. We have 4 plus 2 is 6 already, so we don't need another coefficient in front of this to make sure that iodine is balanced. So as written right now, 4 plus 2 is 6. We have 6 on the product side, so that we wouldn't write the coefficient, but would just be a coefficient of 1. And then what this product specified is to determine the sum of the coefficients on the reactant side. So to add those all up, we get 6 plus 8 plus 4. And then when you're doing problems like this, remember that even though we don't usually write the 1 there, it is implied that there's a coefficient of 1 in front of I2, so don't forget about that one and include it. And so that's one that people often forget because it's not explicitly written there, but it is a coefficient of 1, and that means the sum on the reactant side is 19. Okay? All right, so that's how we balance chemical equations. Like I said, it's mostly just a guess and check or empirical method. We're just we'll learn some more systematic ways of doing it for certain types of reactions in the next chapter. So what we're going to move on to now is one of my favorite topics, which is called stoichiometry. So now that we have balanced chemical equations, and now that we have all these relationships involving moles, we're going to put them together into a big topic called stoichiometry, which is going to cover basically the rest of this chapter as well as a lot of the next chapter. So what's the definition of stoichiometry? Basically what we're doing in stoichiometry is we're calculating the amounts of reactants and products that are involved in a chemical reaction. All right, and there's a lot of ways that we can do this, a lot of possible variants on this, but as an example, if we want to use this many grams of reactant A, we can calculate how many grams of reactant B do we need for those 2 to react completely. Or if we combine this many grams of A and B, how many grams of the product are formed. So a lot of different ways of doing this, but it's going to be in, again, calculating amounts of the reactants and or products that are involved in a chemical reaction. All right, and the key concept in stoichiometry is what are called mole ratios. So as we talked about when we introduced chemical equations a little bit ago, the coefficients in chemical equations can be interpreted in terms of number of moles, the number of moles of each reactant that's involved, the number of moles of each product that forms, and ratios of those coefficients is going to be the key that we need to be able to do stoichiometry. So the coefficients in a balanced chemical equation, so to be able to do stoichiometry, you need a balanced chemical equation first. That's always step one. And then once you have that, we can use the coefficients and interpret them in terms of the number of moles of each reactant or product. All right, so the coefficients in the balanced chemical equation, they tell us the relative number of moles of each reactant and product that's involved. All right, so if we have this hypothetical chemical equation using not real elements and compounds, but just letters to designate each reactant and product, 3A plus 2B equals 4D, what we're going to do in stoichiometry, and again, this key concept being mole ratios, is we are going to set up ratios of these coefficients and basically say that for example, every 3 moles of A that reacts, we're going to need 2 moles of B. And so if we know how much of one reactant we have, we can figure out how much of the other reactant we need. And similarly, we can write a ratio really between any combination of these. So for example, for every 3 moles of A that reacts, we form 4 moles of the product D. And for every 2 moles of B that we react, we form 4 moles of D. So basically these mole ratios come from the coefficients of each reactant and product, and we can invert the ratios if necessary. We can write any combination of coefficients as a mole ratio. And so these are all unit factors that we can use to convert between an amount of one substance in moles and an amount of another substance also in moles. Okay? So these ratios, these mole ratios that I wrote down here, these are all unit conversion factors or unit factors that allow us to convert between amounts of one substance and amounts of another. And we can write them in either way, either in this order, or we can flip the ratio, however it needs to allow us to convert between one another. So what I'm going to do here is sort of, in general terms, diagram the process of stoichiometry. So the most common type of stoichiometry problem, at least at this stage, and one that's very common in chemistry in general, is what's called a mass-to-mass problem. Okay. Now, it's not so important that we classify all these different problems and all that, but what a mass-to-mass stoichiometry, what we're doing is we know the mass of one substance that's involved in a chemical reaction. Again, either a reactant that's involved in the chemical reaction or a product that's formed. And what we want to calculate is the mass of another substance that's involved in that same reaction, either the mass of another reactant or the mass of another product that forms, or anything really, any reaction or product that's involved. And there's no direct way of doing this, right? This is what we want to be able to do. We want to convert mass of one substance that we know into how much of another substance is going to be involved in that same reaction. But there's no direct way to do this because the coefficients in the chemical equation don't tell us the masses of each substance that are involved. They tell us the moles of each substance that are involved. So what we have to do then is we have to first typically convert the mass of substance A, the one that we know, into moles. And as a reminder, the way that we do that is by using its molar mass, either the atomic mass if it's an element, or the molecular mass if it's a compound. So using the molecular weight, we can convert mass to moles. And then once we have moles of a substance, we can use the balanced coefficients, the reaction coefficients, to convert between the different amounts. So by using reaction coefficients, mole ratios that are determined from those coefficients, we can convert the moles of one substance into the moles of another that are involved in that same reaction. And then once we have the moles of substance B, if we want to figure out how much mass of substance B that corresponds to, we can use its molar mass to convert back to its mass amount. Okay? So in a mass-to-mass stoichiometry problem, this is sort of the most common route we take. Mass of one substance into moles, mole ratios or reaction coefficients to figure out the moles of another substance, and then back to mass using the other molar mass. Now, some other variations on this that we'll see is that, remember that we have also the definition of moles in terms of Avogadro's number. So if we wanted to calculate how many atoms or molecules of this reactant or product are in the reaction, we can use Avogadro's number to do that. So again, maybe not super useful or practical in a real lab setting, but something that we can use the definition of moles to allow us to do. And similarly, if we want to know the number of atoms or molecules of the other substance that are involved, we can use Avogadro's number as well once we have moles of that substance. So basically what we're doing in stoichiometry is we're using the mole relationships that we learned last time in combination with mole ratios that we get from reaction coefficients, okay? So let's see how we do this then in a real example. So if we have this reaction here where we're taking gold, nitric acid, hydrochloric acid, and then mixing them together to make what's called hydrogen tetrachloroaurate, nitric oxide, NO, which is nitrous oxide, I think? No, nitrogen monoxide, and then water. So that's the chemical equation. Here we gave it to you. How many molecules of water are formed when 2.56 grams of gold is completely converted into the product HAUCl4? Now this reaction here, the mixture of nitric acid and hydrochloric acid, as a little trivia, is called aqua regia, which is a Latin term for the water of kings, because this mixture of nitric acid and hydrochloric acid is one of the only substances that can dissolve gold. So basically what you're doing in this reaction is you're dissolving gold and converting it into an acid, HAUCl4, and this combination of HNO3 and HCl, which is called aqua regia, allows you to do that. It's called the water of kings because it allows you to dissolve gold, which very, very few other things can actually do. So when we're doing problems like this, we're going to set them up a lot the same way as a lot of the problems we set up last time. So what we're looking for is the number of molecules of water. So we're going to write down what we're looking for. And then we're going to write down what we know, which is that we're reacting 2.56 grams of gold. And we're going to just figure out a series of steps that allow us to get there. Now in a stoichiometry problem, in almost every case, the first thing you want to do is convert into moles. So we don't have moles right now. We're not given moles, so we're going to convert into moles first. Since it's an element, we're just going to use the atomic mass from the periodic table to go from grams into moles. So we want grams to cancel, so we're going to put the atomic mass in the denominator. This is the atomic mass of gold, which we saw last time. You can get it from the periodic table, and that gives us moles. Once we have moles of one substance, we can convert into moles of the other substance using the reaction coefficients. So since we're trying to find how many molecules of water are, the first thing we're going to do is figure out how many moles of water there are. So we want to convert into moles of water from moles of gold. And to do that, we're going to use the coefficients in the balanced equation. So water has a coefficient of 2 in front of it. Gold has no coefficient, meaning there's a coefficient of 1. And so what that means is that 2 moles of water are going to form for every 1 mole of gold that reacts. So that allows us to cancel moles of gold and convert into moles of water. All right, so we have moles of water now, but we don't want to stop here because we're looking for how many molecules of water. And again, to do that, we're going to use Avogadro's number. If we want to find the total number of molecules, we have a conversion that allows us to do that, which is Avogadro's number. Molecules of water per mole of water, and that's just going to be the definition of a mole, which is that there are Avogadro's number, 6.02 times 10 to the 23rd molecules for every 1 mole of water. Moles of water cancel out. We get now to the unit that we're looking for, which is molecules of water, and we can multiply across and find out that we'll get 1.56 times 10 to the 22nd molecules of water. All right, so that would be our final answer, and we'd report it however Blackboard told us to. All right, so this was a typical stoichiometry problem. In this case, though, we want to find molecules of water, not mass of water. Any questions on that? All right, the next thing we'll do is a more typical mass-to-mass stoichiometry problem. And in this problem here, we didn't give you the chemical equation directly, so we're going to have to go ahead and produce that. So iron reacts with, we saw earlier that iron reacts with oxygen to form rust. You can also, under certain conditions, react it with water to form a different iron oxide, Fe3O4, which is called magnetite. As you might imagine, it's magnetic from the name. And we want to know if we have 25 grams of Fe, how many grams of water are required to react completely with that? So in this case, we don't have a balanced equation, so that's the first thing we need to do is write the balanced chemical equation. So we're saying that iron reacts with water, so our two reactants are going to be Fe and H2O water. Hopefully we know that the formula of water is H2O. And they're going to form Fe3O4 magnetite and hydrogen gas, which is H2. Okay? So reactants on the left, products on the right, which we have to read off from this first sentence here. Iron reacting with water, so those are the two reactants, forming magnetite and hydrogens, whatever's formed is the product. And then we're going to balance the equation. We're going to set this to 1. 3 irons, so we need to have a 3 over here. 4 oxygens, so we need a 4 in front of H2O to make oxygen balance. And now that we put a 4 in front of H2O, we have 8 hydrogens on the left. We also want to have 8 on the right, so that's going to also get a coefficient of 4 to make sure that everything is balanced. So since I'm running low on time, I'm not going to go through that, but this would be the balance equation that we get. We can check that there's the same number of each element on both sides of the reaction arrow. Now that we have the balanced equation, which I'll write again here so we have it in front of us, 3Fe plus 4H2O going to Fe3O4 plus 4H2, now we can do the proper conversions. So we want to find out how much water is required to react with 25 grams of iron. So what we're looking for is the grams of water that are going to be involved in this reaction. That's our unknown. And our starting point that we know is that we're reacting 25 grams of Fe. Okay? So this will be a more typical mass-to-mass stoichiometry problem because we're giving you the mass of one reactant and asking you to find the mass of another reactant that's involved in the same chemical equation, same chemical reaction. So the first thing we're going to do, as always, is convert to moles. So if we have grams of an element, we can use the atomic mass to figure out moles. We want grams to cancel out, so we're going to put the atomic mass in the denominator, 55 grams per mole for iron. You'll find that on the periodic table. All right, and then we're going to do, now that we have moles of iron, we can figure out how many moles of water will react with that by using the coefficients. So we can convert from one substance to another. We want moles of water in the numerator and moles of iron in the denominator to cancel out, and we go to the coefficients in the balanced equation. Water has a 4 in front of it, so we're going to need 4 moles of water. Iron has a 3 in front of it for every 3 moles of iron that reacts. So for every 3 moles of Fe, we need 4 moles of water as a reactant as well. Moles of iron cancel. Now we're in moles of water, but we're not quite ready to stop yet because we need to find the grams of water. So to go from moles into grams, moles of water in the denominator, grams of water in the numerator, we're going to use the molar mass of H2O, which is just the sum of the atomic masses, 18. So 18.02 grams of water per mole, that's just the molar mass of water. Moles cancel out. Now we're in grams of water, which is what we're looking for. So we just have to multiply and divide these numbers and find out that we need 10.8 grams of water. Okay? So what this means is that if we want to react all 25 grams of iron, 10.8 grams is the minimum amount of water that we need, the ideal amount that would be necessary to react completely. All right, so I think we're out of time. So what I'll do is I will actually let you guys work this out on your own, and then I'll work it out in the notes before I post them, and next time we'll move on to some other topics related to stoichiometry as well.